Welcome back to Very Ordinary Differential Equations. In this lecture, we learned how to take the Laplace transform of homogeneous linear systems. First, we need to discuss how to take the Laplace transform of a matrix. Now remember, for a function f of t, the Laplace transform capital F of s is defined as the following improper integral, the integral from 0 to infinity of e to the minus st times f of t dt. When f of t is a matrix of functions, the definitions really don't need to change in any way. If s and t are numbers, then e to the minus st is just a scalar. So we can distribute that scalar, e to the minus st, into a matrix f of t, and then integrate every term without any issue. So if we integrate the matrix term by term, we will recover a matrix-valued capital F of s. In other words, taking the Laplace transform of a matrix just means to take the Laplace transform of every term of that matrix. Furthermore, because the Laplace transform is linear, constant matrices can be factored out from this procedure. So if f of t is an n by 1 column of functions and A is an n by n matrix of constants, then the Laplace transform of AF is just A times the Laplace transform of F. We are factoring out the constant matrix A. Our central tool in using Laplace transforms to solve differential equations, remember, was the identity that the Laplace transform of a derivative can be expressed as s times f of s minus little f of 0. We can use this identity in solving y prime equals ay, where we have a system of equations, using the same sequence of steps that we did before. Take the Laplace transform of both sides of the differential equation and use the first identity on the page. Then solve for the Laplace transform of y, take the inverse Laplace transform of both sides, and you'll recover the function y. So we wish to solve the system y prime equals ay. We begin by taking the Laplace transform of both sides. On the left, the Laplace transform of a derivative is s times the Laplace transform minus the initial state of the function you began with. And as we've done before, the Laplace transform of a lowercase letter is going to be represented with an uppercase. On the right, we factor the constant matrix A out, and the Laplace transform of y, we're denoting capital Y of s. Now the goal is to solve for capital Y of s, so we move all the terms with capital Y over to one side and move every term that doesn't have capital Y to the other. Now what we have here is a scalar s times a column capital Y minus a matrix A times the column capital Y. And as we've seen before, we can factor this out as s times the identity minus A times the column capital Y. Now our goal is to solve for capital Y of s. If s is not an eigenvalue of the matrix A, then the determinant of Si minus A is not 0. In other words, the matrix Si minus A is invertible, in which case we simply need to multiply by it to solve for capital Y. So here's where we've gotten in attempting to solve the system y prime equals ay, and provided that s is not an eigenvalue of A, multiply by the inverse of that matrix, and there you have it. Now you just need to take an inverse Laplace transform of both sides. So on the left, you'll recover your solution, y of t, and on the right, y of 0 is a constant column, and it can be factored out of the inverse Laplace transform. So we've managed to express the solution y of t as whatever this matrix is times the initial state y of 0. Matrix multiplication is not commutative, so this order on the right side is important. We factored the constant y of 0 out on the right, not on the left. It's a column, it wouldn't even make sense to factor it out on the left. Just be careful. When dealing with matrices, order of multiplication matters, so factoring things out, it really makes a difference whether you factor things on the left or the right. So here's where we are right now. In solving the system y prime equals ay, we've determined that the solution y of t is the inverse Laplace transform of Si minus A inverse times the initial state y of 0. So we can make the following interpretation of that matrix, inverse Laplace transform of inverse matrix of Si minus A. Once you compute whatever this matrix is, it tells you exactly how to transform the initial conditions y of 0 into the state of the solution at any time t. So it is called the state transition matrix. From your initial state y of 0, you multiply by this matrix of functions, and it tells you what the solution is at any time t. The matrix Si minus A inverse by itself is simply called the resolvent. So this terminology we're going to use. We need to compute the matrix Si minus A and then invert it. The inverse of that matrix is called the resolvent. If you take the inverse Laplace transform of that matrix, that is called the state transition matrix. So in order to find solutions, we need to find that state transition matrix, the inverse Laplace transform of Si minus A inverse. So before we can take the inverse Laplace transform, we need that resolvent Si minus A inverse. When A is a 2 by 2 matrix, we can rely on the following formula for determining inverse matrices which are 2 by 2. Okay, so this is a formula that is handy to know exists and to look it up when you need it. For larger matrices, however, we're going to be using Cramer's rule. If you wish to compute Si minus A inverse, and you need to know the ij entry, so this is the ith row and jth column of whatever this inverse matrix is, it can be computed as -1 to the I plus j times the determinant of delta ij over the determinant of Si minus A. Delta ij is the Si minus A matrix where you remove the ith column and jth row. And this is a little confusing and easy to get mixed up. In attempting to compute the ith row and jth column of this matrix, you remove the ith column and jth row from the matrix Si minus A and compute a determinant. As our first example, compute the state transition matrix of the system and then solve y prime equals this matrix times y. So first we compute Si minus A. Well, Si minus A, we just have s's on the diagonal and we subtract the matrix A. So there it is, s minus 1, 6, 2, s minus 2. Now what we have to do is find the inverse matrix. So for 2 by 2 matrices, remember, we're going to rely on this formula here. Using the formula from the previous slide, the inverse of s minus A is 1 over its determinant, s minus 1 times s minus 2 minus 12. Then you switch the two entries on the diagonal and you multiply by -1 on the off diagonal. That determinant is s squared minus 3s minus 10, which factors as s minus 5 times s plus 2. So here is Si minus A inverse. It's this matrix where every entry has to be divided by s minus 5 times s plus 2. So we've computed the resolvent matrix as follows. We're going to distribute the determinant of Si minus A as a denominator into this matrix and get the following. So here is our resolvent matrix, the inverse of Si minus A. We know we're going to have to take an inverse Laplace transform, which means we're going to need to perform partial fraction decomposition of every term. Now with the aid of a computer, here we have it. Here is every term of the resolvent matrix with partial fraction decomposition applied. Now we're going to need to take the inverse Laplace transform of this matrix. So here's the resolvent matrix after applying partial fraction decomposition. So we can take the inverse Laplace transform of this matrix and then multiply by the initial state on the right. Inverse Laplace transform here is pretty quick. Notice that there's a common denominator of 7 to everything, so we're going to go ahead and factor that out. Otherwise, inverse Laplace transform of 4 over s plus 2 is 4e to the minus 2t. Inverse Laplace transform of 3 over s minus 5 is 3e to the 5t, and so forth. So having gone through all of the tedious work of the partial fraction decomposition, the inverse Laplace transform is pretty straightforward in this example. And don't forget to multiply on the right by your initial state, the column y of 0. So we've managed to compute that y of t is the matrix 1/7 times all of these exponential terms times a column given by your initial state y of 0. If we go ahead and write y of 0 is y1 of 0 and y2 of 0, then the top entry, y1 of t, would be 1/7 times this entry times y1 of 0, there we have it, plus this entry times y2 of 0, and there it is. Similarly, the bottom row would be given by 1/7 times this entry of the state transition matrix times y1 of 0, plus this entry of the state transition matrix times y2 of 0. So there those are. So we've written y1 and y2 of our solution in terms of the initial values. We can distribute some things and collect according to exponentials, which would be a little more typical. So instead of writing everything in terms of what is multiplying y1 of 0 and what is multiplying y2 of 0, it might be more standard to write what is multiplying the exponential e to the minus 2t and what is multiplying the exponential e to the 5t. For our second example, solve an initial value problem. Well, we begin by computing the state transition matrix. So first we have to compute Si minus A. There it is. We have to find an inverse of it. In other words, we have to find the resolvent matrix. Since this is a 2 by 2 matrix, we rely on the previous formula. 1 over the determinant of Si minus A. So S minus 3 times S minus 1 minus negative 1 times negative 2 simplifies like this. Then switch the elements on the diagonal and multiply the off diagonal by minus 1. There's your quick way to invert a 2 by 2 matrix. So here's our resolvent, Si minus A inverse. Once we go ahead and distribute in that denominator, notice this denominator is of the form S minus 2 squared. Now that would give me a plus 4, so I need to subtract root 3 squared. In other words, subtract 3. So distribute that denominator in. We're putting it into this form, by the way, because we happen to know we're going to have to take an inverse Laplace transform, and this is a form that we can find on a table of Laplace transforms. We actually don't need to do any partial fraction decomposition in this matrix. They're all simplified already. However, when we're taking an inverse Laplace transform, we want our numerators to either be constants, which is fine here and fine here, or of the form s minus 2. So here we have s minus 1, and here we have s minus 3. We'd really like to have an s minus 2 instead. So instead of writing s minus 1 up here, we call it s minus 2 plus 1. And instead of writing s minus 3, we call this term s minus 2 minus 1. So now it wasn't partial fraction decomposition, but we did do a little bit of manipulation so that every term is now of a form that we can recognize in a table of Laplace transforms. So we can get our state transition matrix by taking the inverse Laplace transform of this resolvent matrix. And here we have it. Okay, we've got a bunch of hyperbolic sines and cosines floating about. So now we have the state transition matrix by taking the inverse Laplace transform of the resolvent matrix. Here it is. Then y of t, our solution, is given by the state transition matrix times y of 0. With our known initial values of negative 1 and 2, we can actually simplify that down to this right here. Now, if we had solved for the general solution using earlier techniques, we would have computed eigenvalues of this matrix here, and those eigenvalues will be irrational. That will make finding eigenvectors a little inconvenient. Not impossible, just inconvenient. Notice, however, that the solution we found by taking Laplace transforms does have irrational exponentials in here. This hyperbolic cosine and hyperbolic sine involve terms of the form e to the root 3 times t. So there are irrational exponentials built into the solution we found here. If you solve this by finding eigenvalues of the matrix and then eigenvectors, your solution will look a little bit different. It will be explicitly in terms of those exponentials. For our third example, solve this initial value problem. Now we have to compute the resolvent matrix Si minus A inverse. But because we have a 3 by 3 matrix this time, we're going to use Cramer's rule. So here's Si minus A. We have S's on the diagonal, and then you subtract the matrix A. Using Cramer's rule can be a bit tedious, and we're going to do this quite explicitly for the top row of inverting this matrix. So consistently in every term, what we do need is the determinant of Si minus A. So the determinant of Si minus A, relying on a computer algebra system, factors as S minus 2, S minus 1, S plus 3. So if you compute the determinant of this 3 by 3 matrix, it should factor like that. All right, so here's Si minus A. Si minus A inverse entry 1, 1 is, by Cramer's rule, negative 1 to the 1 minus 1 the determinant of what we called delta 1, 1 times the determinant of Si minus A. Now, delta 1, 1 is the matrix formed by removing the first column and first row. So if I remove the first column and the first row, what is left behind is the matrix here, S plus 3, 11 minus 1, S plus 3. So we need to compute the determinant of that matrix, which is just S squared plus 6S minus 20. We need to divide by the determinant of Si minus A, which on the previous slide we mentioned was given by S minus 2, S minus 1, S plus 3. We happen to know also that we're going to need to do partial fraction decomposition to every term. And again, with the aid of a computer system, the partial fraction decomposition of this rational function right here is given as follows. So we have now computed the entry in the first row, first column of the resolvent matrix. Next, we move on to the first row, second column of the resolvent matrix. According to the formula, we have to compute negative 1 to the 1 minus 2, the determinant of delta 1 comma 2 over that same determinant of Si minus A. Now, delta 1, 2 is formed by removing not the first row and second column, but the first column and second row. So if we delete the first column and we delete the second row, what's left behind is negative 1, negative 11, negative 1, S plus 3. There it is. We also have to multiply by a negative 1 because we have an odd power up here. So the determinant of this matrix can be quickly computed as S plus 14, and it is still being divided by the determinant of Si minus A. Again, we do need to do partial fraction decomposition with the aid of a computer. Here's the partial fraction decomposition of that term. Next, we're going to compute entry 1, 3. This is the first row, third column entry of the resolvent matrix Si minus A inverse. So here is the formula we're going to use from Cramer's rule. This delta 1, 3 is formed by removing the first column and third row, leaving behind negative 1, negative 11, S plus 3, 11. There it is. We have an even power up here, so we don't need a minus 1 out in front. And when we compute this determinant, we get 11S plus 22. We're still being divided by the same determinant of Si minus A. We apply partial fraction decomposition, and here's that entry of the resolvent matrix. So we keep going in this manner. Every entry of the resolvent can be computed like this. We have to apply partial fraction decomposition to every term. It's quite tedious, but here's the result. So here is our resolvent matrix having applied partial fraction decomposition to every term. Now what we have to do is take the inverse Laplace transform of this resolvent to give us the state transition matrix. Now, the benefit is the hard work is actually done. To take an inverse Laplace transform of all of this, notice that all of our terms are something over S minus 1, something over S plus 3, something over S minus 2. The inverse Laplace transform of these are e to the t, e to the minus 3t, and e to the 2t respectively. So we just go through term by term and knock out all of these inverse Laplace transforms. Once you do that, here's what you'll get. Okay, so we have taken an inverse Laplace transform of the resolvent matrix. This is now called the state transition matrix. The solution to our differential equation is then given by the state transition matrix times your initial column y of 0, which was explicitly given to us at the beginning of the problem. All in all, what have we discussed? We can take the Laplace transform of a matrix. Therefore, Laplace transforms are still a way that we can solve differential equations when matrices are involved, in other words, first-order linear systems. In fact, we can use the Laplace transform on a matrix of functions, so it can even be used on a system with non-constant coefficients. But if the matrix A is not a constant, it can't factor out of the Laplace transform like this. When A is a matrix of constants, however, the general solution to our linear first-order system with constant coefficients, y prime equals ay, is given by the state transition matrix, which is the Laplace transform of Si minus A inverse, times your initial conditions y of 0. So we end up with a linear operator, the state transition matrix, acting on your initial conditions y of 0, and there's your solution for the linear first-order homogeneous system with constant coefficients.